A small clay cone sits in the palm of an ancient accountant. It is not impressive. It is smaller than a grape, baked the color of dry earth, and shaped by fingers that disappeared thousands of years ago. There are no equations on it. No familiar digits. No plus sign. No zero. Yet objects like this helped create something stranger than writing. They helped humans separate quantity from the world. Before that separation, 3 sheep were 3 sheep. 3 baskets of grain were a different problem. 3 days were something else again. The astonishing step was realizing that all of them shared an invisible property. Strip away the wool, the grain, the sunrise, and something remains. 3. Numbers feel so fundamental that it is difficult to imagine anyone inventing them. Rocks exist without us. Trees exist without us. 3 rocks seem to exist whether anyone counts them or not. But a number system is different. Nature gives us collections. Human minds turn those collections into exact, reusable abstractions. Then human societies give those abstractions names, marks, rules, positions, signs, tables, algorithms, and eventually machines. That process did not happen once. It unfolded in different ways across Africa, Mesopotamia, Egypt, China, India, Mesoamerica, and many other regions. It took tens of thousands of years, and one of its most important breakthroughs was not learning how to represent something enormous. It was learning how to represent nothing at all. Long before humans had numerals, they already had a rough sense of quantity. Modern cognitive research finds versions of this ability in newborn babies and many non-human animals. A person does not need mathematics lessons to glance at 2 groups and notice that one contains far more objects than the other. A monkey can make quantity judgments. So can some birds and fish. This ancient ability is approximate. 8 pieces of fruit versus 16 is fairly easy. 8 versus 9 is harder. The closer the quantities become, the less reliable the intuition becomes. That is not counting. Counting gives something evolution alone did not hand us: exactness. The difference between 27 animals and 28 may be almost invisible to the eye. If one of them belongs to someone else, however, that difference can suddenly matter very much. Exact number requires a way to make quantity survive after the objects disappear. Imagine a hunter returning to camp and wanting to remember how many animals crossed a trail. One possible solution requires no number words at all. Make one cut in a stick for each animal. Animal. Cut. Animal. Cut. The marks preserve a one-to-one relationship. Hours later, the animals may be gone, but their quantity remains recorded in wood or bone. Archaeology has produced tantalizing objects that may reflect this kind of behavior. The Ishango bone found in what is now the Democratic Republic of Congo is around 25,000 years old, according to the Smithsonian Human Origins Program. Its surface carries organized groups of notches. What those groups meant is unknown. Some researchers have proposed arithmetic patterns. Others have suggested tallying or calendrical functions. More ambitious claims have seen multiplication, division, or prime numbers in the marks. The bone cannot tell us which interpretation is correct. That uncertainty matters. A sequence of cuts is evidence that somebody deliberately recorded something. It is not automatically evidence that its maker understood mathematics in the modern sense. The safest conclusion is also the most interesting one. Long before writing, people were externalizing quantity. Memory had started moving out of the brain and into objects. A tally solves one problem beautifully. It remembers exact quantity. But it has a weakness. If a shepherd owns 487 animals, carving 487 marks is possible, but inconvenient. If a storehouse receives thousands of measures of grain, the problem becomes worse. A society can keep adding marks, but eventually it needs compression. Human bodies may have provided part of the answer. Hands make remarkably useful counting devices. 10 fingers encourage groups of 10. In some traditions, fingers and toes support groups of 20. Other techniques can use finger joints and phalanges to track larger quantities. This probably helped shape some number bases, but there was no universal prehistoric committee choosing decimal notation. Human cultures developed systems based on 5, 10, 20, 60, and combinations of several bases. That diversity tells us something important. Quantity may be universal. Numeral systems are cultural technology. The pressure to improve that technology became much stronger when human communities became larger, more settled, and more economically complicated. A mobile group can remember a great deal through personal relationships. A village storing harvests has different problems. How many containers entered the granary? How much seed must remain for planting? Who contributed livestock? Who received a ration? Who owes what? Now, quantity is no longer merely useful information. It can determine survival, obligation, wealth, and power. Across the ancient Near East, people began using small clay counters. The system developed over millennia. Researchers have documented tokens from roughly the 8th millennium BCE onward, long before full writing appeared. Different shapes could correspond to different categories of goods or quantities. Cons, spheres, discs, cylinders, and more complicated forms created a physical vocabulary for accounting. The crucial feature was that the account could travel separately from the goods. A flock could be elsewhere. Grain could already be inside a building. The tokens preserved information about the transaction. Humans had created a portable model of an economy. Then administrators made the system even stranger. Some tokens were sealed inside hollow clay envelopes, often called bulli. The container could preserve a transaction and its seal could help authenticate it. There was an obvious inconvenience. Once the counters were sealed inside, you could not see them without breaking the container. One solution was to press token shapes onto the wet surface before sealing them away. Now the outside displayed information about what was inside. At some point, the physical counter became less necessary. Why place a token inside clay when its impression could carry the information? A three-dimensional accounting object could collapse into a two-dimensional mark. That transition takes us toward the earliest writing of southern Mesopotamia. By the late 4th millennium BCE, cities such as Uruk had become enormous by earlier standards. Institutions collected grain, redistributed food, organized labor, managed herds, and tracked commodities moving through an increasingly dense economy. The bookkeeping became correspondingly complex. Clay tablets from around 3300 BCE contained pictorial signs and numerical impressions. Early writing was heavily administrative. It recorded commodities, allocations, deliveries, and quantities, before scribes used writing to preserve long works of literature. Numbers were helping create writing because organizations needed memory larger than any one administrator. Yet something even more profound was happening inside the notation itself. Early Mesopotamian accounting often used different numerical conventions, depending on what was being counted or measured. Grain, animals, areas, and other commodities could belong to different metrological systems. This was not yet the clean modern world in which the digit 5 remains 5, whether it refers to kilograms, dollars, or planets. The long intellectual movement toward abstract number involved detaching quantity from a specific kind of object. That is one of the deepest inventions in this entire story. Once 7 can exist independently, it can attach itself to anything. 7 sheep. 7 jars. 7 workers. 7 days. 7 stars. The objects no longer define the number. The number describes the objects. That sounds obvious only because thousands of years of culture have trained us to make the leap automatically. A young child has to learn it. Humanity did too. Numerals are therefore a compression technology. Instead of keeping 73 pebbles, you can preserve a sign meaning 73. Instead of physically matching each sheep against a counter, you can write a quantity that survives changes in the flock. That compression becomes more powerful when societies find efficient ways to write large values. Ancient Egypt developed a decimal numeral system using distinct hieroglyphic signs for powers of 10. There were signs for 1, 10, 100, 1000, and larger powers. Repeat and combine them, and a scribe could record substantial quantities. The system suited an administration concerned with grain, land, labor, taxation, and construction. By about 1550 BCE, the Rhind mathematical papyrus shows Egyptian scribes working through more than 80 problems involving multiplication, division, fractions, areas, and volumes. Numbers were no longer merely labels. They were things you could operate on. But Egyptian notation was not a positional decimal system like ours. A sign did not acquire its value simply because it occupied the tens column instead of the hundreds column. That distinction becomes crucial. Consider how modern notation works. In 555, the same symbol appears 3 times. Yet the first 5 means 500, the second means 50, and the last means 5. The mark itself has not changed. Its location has. This is one of those inventions that becomes nearly invisible once learned. Position creates magnitude. With a tiny set of symbols, you can write numbers far larger than anything a person could physically tally. Ancient Mesopotamian mathematicians developed an extraordinarily powerful version of this principle. Babylonian mathematics used a place value system based on 60. Instead of our columns representing ones, tens, hundreds, and thousands, Babylonian positions could represent powers of 60. The origin of the sexagesimal tradition is still debated. 60 has obvious practical advantages because it divides evenly by many smaller integers, including 2, 3, 4, 5, and 6. But that does not prove ancient people deliberately chose it for that reason. The system appears to have grown out of earlier counting and measurement practices. Whatever its origin, the result was formidable. Old Babylonian scribes could calculate multiplication, division, areas, reciprocals, and square roots with remarkable accuracy. A famous tablet, known as YBC 7289, preserves an approximation of the square root of 2. Written in sexagesimal place value, its precision is close enough to surprise anyone expecting Bronze Age mathematics to consist only of crude counting. The important invention was not simply base 60. It was place. Place value turns notation into a calculating machine. But it immediately creates a dangerous question. What happens when a place contains nothing? Suppose one position has units, and another has 60 squared units, but the position between them is empty. If you simply leave a gap, how wide must the gap be? And what happens when handwriting compresses it? Early Babylonian notation lived with ambiguity. Context and spacing often carried information. Later, Babylonian scribes introduced a special mark for an empty internal position. That symbol behaved somewhat like a zero placeholder, but it was not yet R0. That distinction is essential. There is a major conceptual difference between saying, "nothing occupies this position," and saying, "nothing is itself a number with which I can calculate." Human beings reached those ideas at different times and in different places. China developed another exceptionally effective computational tradition. By the last centuries BCE, Chinese mathematicians were using counting rods on boards. Rod arrangements represented decimal digits, while their positions represented units, tens, hundreds, and higher powers. A blank position could perform the job that a written zero later performs. More importantly, the rods were movable. Calculation happened physically. Numbers could be placed in rows and columns, rearranged, reduced, added, and subtracted. In this sense, the counting board was both writing surface and computing device. The mathematical text known as the 9 Chapters on the Mathematical Art, assembled from older traditions and later commented on by Lu Hui in 263 CE, presents algorithms for surveying, taxation, trade, engineering, fractions, and systems of simultaneous equations. It also uses something that troubled mathematicians elsewhere for centuries: negative quantities. Negative 3 sheep make little sense if a number must always describe a pile of physical objects. Debt changes the picture. If possession can be represented as one direction and obligation as another, quantities can pass below nothing. Chinese calculating traditions distinguished positive and negative values using differently colored rods. The mathematics was tied to practical situations involving gains, losses, and equations. Here again, commerce helped force abstraction. A number no longer had to mean how many objects are here. It could mean a relationship, a deficit, a direction, a missing amount. That is a much bigger universe. Meanwhile, on the other side of the world, Mesoamerican mathematicians developed a different solution. Maya mathematics used a vigesimal, or base 20, structure. Dots represented ones. Bars represented fives. A shell-like sign represented 0. The notation supported enormous calendrical counts. The Maya long count tracked days through nested units extending across vast periods of time. Astronomical and calendrical calculations could locate events within cycles stretching far beyond an individual human life. This tradition arose independently from the mathematical systems of Eurasia. That alone destroys any simple story in which numbers were invented once and handed from civilization to civilization. Humans repeatedly invented ways to turn quantity into durable symbols because different societies faced variations of the same problem. Things disappear. Memory fails. Transactions multiply. Time passes. Symbols remain. The next transformation in our own modern numeral system took shape in South Asia. Indian mathematicians developed decimal place value notation, using a family of numeral symbols that ultimately became ancestors of the digits used across much of the world today. The history is complicated, and no single surviving document captures the moment of invention. One famous piece of evidence is the Bakhshali manuscript, a mathematical work written on birch bark and found in the 19th century near what is now Peshawar, Pakistan. The manuscript contains a dot used as a placeholder. Radiocarbon tests on several pieces of its bark produced dates from different centuries, demonstrating that the surviving manuscript is composite and complicating attempts to assign one date to the whole text. That makes claims about the first zero hazardous. But the broader transformation is clear. In the Indian decimal system, the empty position was on its way to becoming something more powerful than punctuation. In 628 CE, the mathematician and astronomer Brahmagupta wrote the Brahmasfuta Siddhanta. There, zero was treated as a mathematical quantity and placed inside explicit arithmetic rules. Add zero to a number, and the number remains unchanged. Subtract a number from itself, and the result is zero. Multiply a number by zero, and the result is zero. Brahmagupta also formulated rules involving positive and negative quantities, which he described through ideas comparable to fortunes and debts. He did not get everything right. His attempt to handle division by zero did not produce the modern rule that division by zero is undefined. And that failure makes the episode more revealing, not less. Zero did not arrive fully formed. Mathematicians had to discover its consequences. Nothing had become an object of thought, and now that object had to obey rules. The invention sounds almost philosophical, because it was. A farmer can show you 5 goats. Nobody can show you 0 goats. They can show you an empty enclosure, but the enclosure is still there. Zero is not an object inside the world. It is a statement about the absence of objects from a category. Then mathematics goes further. Zero can sit between positive and negative numbers. It can occupy a place. It can be added. It can be subtracted. It can transform the value of another symbol simply by standing beside it. Place a 0 after 1 in our decimal system, and you have 10. Add another, and you have 100. Nothing, carefully positioned, manufactures scale. Indian mathematical ideas moved westward through networks of scholarship and trade. During the early 9th century, the scholar Muhammad ibn Musa al-Khwarizmi wrote about calculation using Indian numerals. His works helped transmit decimal positional arithmetic through the Islamic intellectual world. His own name would eventually leave an unexpected descendant in European languages. Algorithm. A personal name became a word for a systematic procedure. That is fitting because the new numeral system mattered less for what the digits looked like than for what people could do with them. Calculation became easier to record and reproduce. Merchants could multiply prices. Astronomers could manipulate tables. Surveyors could process measurements. Students could follow procedures on a page instead of relying entirely on physical counters. Knowledge could travel as method. Europe did not immediately discard Roman numerals. Technology almost never spreads merely because it is elegant. People already knew how to use Roman notation, counting boards, and Abasi. Institutions had established habits. Merchants cared about whether a system was trusted, teachable, and useful, not whether historians centuries later would judge it mathematically superior. The transition took time. Around 1202, Leonardo of Pisa, better known as Fibonacci, completed Liber Abaci. He had encountered the mathematics of the Mediterranean commercial world and promoted what we now call Hindu-Arabic numerals for calculation. His examples were not limited to theoretical puzzles. He dealt with exchange rates, profit, interest, weights, measures, and partnership problems. That was exactly where the new notation was strongest. A positional decimal system could turn arithmetic into written procedure. The digits could move with merchants. And merchants had strong incentives to learn anything that made complicated calculation faster. The numeral revolution therefore spread not simply through mathematicians admiring beautiful ideas. It spread through work. Accountants, traders, surveyors, tax collectors, navigators, astronomers, and teachers made the system useful enough to survive. Eventually, printing helped standardize the shapes of the digits. Mathematical notation continued growing around them. Fractional notation improved. Decimal fractions became increasingly practical in early modern Europe. Algebra acquired more systematic symbols. The page became a workspace in which quantities could interact without any physical counters at all. By then, numbers had escaped almost completely from the objects that originally gave them meaning. A negative number could represent debt. A fraction could represent part of an imagined unit. An irrational number could describe a magnitude that no ratio of whole numbers exactly captures. Coordinates could represent a location. Probability could represent uncertainty. An equation could describe something that had not happened yet. Numbers were becoming models of possible worlds. That power came with a political edge. Counting is never merely innocent once institutions begin doing it at scale. Ancient administrations counted grain because grain could be collected. They counted labor because labor could be assigned. They measured land because land could be taxed. States later counted households, soldiers, births, deaths, and property. Numbers make populations legible. A person can become an entry in a ledger. A harvest can become a tax estimate. A soldier can become part of a manpower total. A worker can become a wage. The same abstraction that allows fair division can also allow impersonal control. This has been true from the first accounting tablets onward. Numbers can protect people too. A written debt can limit what a creditor claims. A measured ration can expose theft. A standardized weight can make trade less dependent on trust. A census can reveal where services are missing. Medical statistics can expose a pattern invisible in individual cases. The power does not belong to numbers themselves. It belongs to whoever chooses what to count, how to count it, and what decisions will follow. By the modern era, number systems had become part of the infrastructure of science. Telescopes produced measurements. Navigation required tables. Finance required increasingly complicated arithmetic. Engineering translated physical forces into quantities. Modern physics went further, turning nature into relationships written mathematically. And then numbers acquired machines of their own. Digital computers represent information using states conventionally written as 0 and 1. The scale is new. The underlying trick is ancient. Position still matters. A bit has meaning partly because of where it sits. Long strings of simple symbols represent enormous quantities, instructions, colors, sounds, letters, and images. The clay accountant and the microprocessor are separated by more than 5,000 years, but they share a principle. Information can be removed from the thing itself, encoded in a symbolic system, manipulated according to rules, and reconstructed somewhere else. Numbers were one of humanity's earliest great encoding technologies. And that brings us back to the original question. How did humans invent numbers? Not by waking up one morning and discovering that 1, 2, and 3 existed. The process happened in layers. First came an ancient biological ability to distinguish more from less. Then people created exact correspondences. One object, one mark, one animal, one counter. Those records let quantity survive outside memory. Growing economies turned counters into administrative systems. Symbols compressed repeated marks. Numerals began separating quantity from commodity. Place value allowed a small collection of symbols to express enormous ranges of numbers. Different civilizations developed different bases and computational tools. Blank positions created a problem that Babylonian, Chinese, Maya, and Indian traditions approached in different ways. And in South Asian mathematics, 0 ultimately became not merely an empty place, but a number governed by arithmetic rules. From there, positional decimal arithmetic traveled, changed, and spread through scholarly and commercial networks until the digits became so ordinary that much of the world forgot they had a history. There was no single inventor. There could not have been. Number is not one invention. It is a stack of inventions built on top of a very old human capacity. The tally is an invention. The numeral is another. Abstract number is another. Place value is another. 0 is another. Negative numbers are another. The written algorithms that manipulate them are another. Put them together, and humans can count things that are not present, calculate things that do not yet exist, and describe things no eye could ever count directly. The population of a country, the distance to another galaxy, the age of the universe, the probability of rain, the balance in a bank account, the number of instructions a processor performs in a second. All of them descend from the same strange decision. Quantity can be represented by something that is not the quantity itself. And perhaps that is the real invention. Not counting. Abstraction. Humans discovered that a mark could stand for an object. Then that a symbol could stand for any collection of objects. Then that symbols could obey rules of their own. Eventually, the symbols became powerful enough to describe parts of reality that human senses could never directly experience. There is one final irony. Many decimal traditions probably owe at least part of their history to the simplest counting device humans carry everywhere. 10 fingers. Those fingers can hold only 10 obvious units at a time. The notation they helped inspire can describe numbers with millions of digits. And somewhere between your fingers and that impossible scale sits the strangest digit of all. 0. The mark that represents no objects. The placeholder that keeps every other place where it belongs. The number that ancient accountants did not need until positional notation made absence important. The symbol beneath much of modern computation. The next time your thumb taps a 0 on a phone, almost nothing happens physically. One piece of glass senses, one touch. But behind that touch is a chain stretching from carved bones and clay counters to Babylonian tablets, Chinese counting boards, Maya calendars, Indian mathematics, Islamic scholarship, European merchants, and digital machines. Thousands of years were required to make that tiny mark obvious. You press 0, and the system knows exactly where nothing belongs.